Hello everyone, this video is going to be a quick exam key for the exam 2 from fall 2014. So we'll start off with a true and false. The first one says if A is a n by n matrix and determinant of A is equal to 0, then A is not invertible. And this is true. Now, this is one of the properties of determinant. One way we can kind of remind ourselves about this one would be to look at the 2 by 2 case. If we have A, which is a matrix A, B, C, D, then we have a formula for the inverse of A. It would be 1 over the determinant of A times the matrix D, negative B, negative C, A. And notice we're dividing by that number value of the determinant of A. So if the determinant of A was equal to 0, this would identify, and therefore there wouldn't be an inverse. So this is one way you can kind of remind yourself about this property. Part B says if A is a n by n matrix and 0 is an eigenvalue of A, then the matrix is not invertible. This is also true. So let's look at this one. The eigenvalue-eigenvector equation looks like AX equals lambda x. Now if we're taking 0 to be an eigenvalue, then this would simplify down to AX equals the 0 vector. But if A was invertible, then this vector would have to be 0, and 0 is not an eigenvector. We're looking for non-zero vectors here that satisfy this equation. So if lambda is 0, then A cannot be invertible. The next one says a n by n matrix must have n distinct eigenvalues to be diagonalizable. That is false. We do need n eigenvectors. That is true, but not eigenvalues. We can have repeated eigenvalues, and sometimes they're diagonal, and sometimes they're not. It depends if we get enough eigenvectors in each eigenspace. D, if A is invertible, then the dimension of the column space of A is equal to n. So in this case, we're talking about an n by n matrix. So therefore, we have this n by n. And for this to be invertible, we'd have to have n linearly independent columns. But if they're linearly independent columns, then all n of them would form a basis for the column space. Therefore, the dimension of the column space would be n. So this one is true. E says elementary row operations on A do not change eigenvalues. And that is false. They do potentially change eigenvalues. So we can't do row operations on A to simplify to help us find eigenvalues and eigenvectors. If we wanted to simplify things, we would have to work with the matrix A minus lambda I. And that's no easier to work with than just calculating the eigenvalues and eigenvectors directly. And this follows right on with B, or for F. If A and B differ only by row operations, and A and B have the same eigenvalues, that is false because row operations do potentially change the value of eigenvalues. 2, let the following set of vectors be a basis for a vector space. Then answer the following questions. The first one is, what is the dimension of V? Well, the dimension of a vector space is the number of vectors in its basis. So if they're giving us a basis that has 2 vectors, the dimension of V must be 2. Next question is this vector, 147, in V? Well, if it's in V, then I should be able to represent it as a linear combination of the basis vectors. So that means there must be some C1 and C2 where I can take that linear combination of these basis vectors and somehow get to 147. Of course, this is a vector equation, which is the same thing as a matrix equation. And either way, I'll just solve it by looking at the augmented system. It looks like this. So I'm going to row reduce this and see if there are solutions or not. So I'm going to leave my first row the same. I'll take R2 minus R1 to get 0, 1, 3. And then I'll take R3 minus R1 to get 0, 2, and 6. Then I will take R3 minus 2 times R2. I have 1, 1, 1 in my first row, 0, 1, 3 in my second row, and 0, 0, 0 in my final row. Then one last step will be to take R1 minus R2. My last row stays the same. My second row stays the same. And I get R1 minus R2 is 1, 0, negative 2. And so for the solutions, the correct weighting of the basis vectors that get me to 147 would be negative 2 times the first vector plus 3 times the second vector. And that will bring me to 147. And part C says, what are the coordinates of x in terms of this basis? So that's how that's written. And really, that's just asking for those values for C1 and C2. It's what are the weightings of the basis vectors that bring us to this vector. So in this case, my coordinates in terms of this B basis would be -2, 3. Now notice the coordinates here only have two components. It's going to have one component for each of the basis vectors that I'm working with. All right, number 3 says, given this matrix, answer the following questions. The first one says, the null space of A is a subspace of R what? Well, the null space is a set of all solutions to the homogeneous equation, AX equals 0. Now we have this matrix up here, which is 2 by 5 matrix. So if I'm looking for possible x's where I can take A times x, they have to have 5 components. X must live in R5. So that means the null space of A, a subset of all those x's, must be a subspace of R5. It says find a basis for the null space. Once again, this is just the set of all solutions to the homogeneous equation. So I'm just going to solve that. Now to solve that, I would really write out that matrix A. I would really write out this matrix, augmented with 0, and find the solutions. But because that right-hand side is 0, it won't change as I do row operations, I really don't even need to show that augmentation. Furthermore, if I look at this matrix A, it's already in RREF. So it's already ready to write out the solutions. So I'm just going to look at the equations that I would generate here. It would be 1 times x1 plus 2 times x2 plus 3 times x4 plus x5 equals 0. So that first row would give me as an equation. And the second one would give me 0x1 plus 0x2, 1x3 plus 4x4 plus x5 equals 0. And it looks like I have free variables for x2, x4, and x5. So I look at those columns, there aren't any pivot positions in those columns, so those are marking my free variables. So my solution, which will look like x1, x2, x3, x4, and x5, a 5-component vector. Well, x1 could be equal to minus 2x2 minus 3x4 minus x5. x2 is a free variable. x3, I can solve this equation for x3 to get minus 4x4 minus x5. And I have x4 as a free variable and x5 as a free variable. And then lastly, I'm going to write this out in terms of the free variables. So this would be x2 times -2, 1, 0, 0, 0, plus x4 times -3, 0, -4, 1, 0, and lastly plus x5 times -1, 0, -1, 0, and 1. Now, I'd really encourage you, if you're not understanding where this parametric vector form of the solution comes from, is to work it backwards. To write this out, multiply each of those vectors by the x2 or the x4 or the x5, and then add the 3 vectors together, and you'll see that it gives us exactly this. It's just a different form of the solution. But what it tells me that the solutions, any solution is just a linear combination of these 3 vectors. Therefore, those vectors are a basis for my null space. So the basis would look like -2, 1, 0, 0, 0, -3, 0, -4, 1, 0, and -1, 0, -1, 0, 1. So this would be the basis for my null space. And then part C says, what is the dimension of the null space? Once again, the dimension is the number of vectors in my basis. So here's my basis. It has 3 vectors. The dimensions of the null space is 3. D says, the column space of A is a subspace of R what? Well, the column space is a linear combination of the columns of A. And each of these columns you can think of as a 2-dimensional vector, a vector with 2 components. So if I add up a bunch of vectors in R2, the result will also be in R2. So that means the column space of A must be a subspace of R2. And it says find a basis for the column space. Well, really, the column space is the set of all linear combinations of all the columns of A. So you might think right away that basis should be 5, because I'm taking a linear combination of these 5 vectors. The problem is these vectors are not linearly independent. Therefore, they don't actually form a basis for the column space. So what I want to do is just find the linearly independent vectors. And these are marked as the pivot columns. The pivot columns are the linearly independent columns of A. So I have 1, 0, and 0, 1. Next part says, what is the dimension of the column space? Well, I have 2 vectors in the basis, so therefore the dimension is 2. And then as a quick check, I should be able to see that the dimension of the column space of A plus the dimension of the null space of A should give me n, as in the number of columns of our matrix A. And sure enough, I do get 5. All right, number 4 has us calculate some determinants of the following matrices. So the first one, we're going to use our formula. The determinant is 4 times 1 minus, that's this product, 4 times 1, minus this product, which is negative 1 times 2. So I have 4 plus 2, which should be equal to 6. Now the next one is a 3 by 3 matrix. And while I can go right ahead and do the full expansion to find the determinant, I do notice one thing right away. I notice that row 1 and row 2 are just linear combinations of each other. The fact that I have rows that are linear combinations of each other tells me this matrix can't be invertible. If the matrix is not invertible, that tells me the determinant of the matrix is equal to 0. Now, of course, if I didn't see that, I can go through the full expansion here. I'm going to expand along the first row. That'll give me 1 times a subdeterminant, this subdeterminant right here, 4, 2, negative 1, and 7. Then I have minus that second value, minus 2, times the subdeterminant where I eliminate that row and column. So I'm left with 2, 2, 3, 7. That's 2, 2, 3, 7. And then I go plus 1. So it's plus, minus, plus along that first row. And then the subdeterminant here, when I eliminate the first row and third column, I'm left with just 2, 4, 3, negative 1. Now I can calculate each of these pieces. This is 28 plus 2, minus 2 times 14 minus 6, plus 1 times negative 2 minus 12. So I have 30, and inside the parentheses here I would get 8, so this is negative 16. And over here I'm going to get minus 14. And so 30 minus 16 minus 14 is 0. So I can show it the long way as well. Now I go to the last one, and you might think, ugh, 4 by 4, this is going to take me a long time to expand. But what I see here is this matrix is upper triangular. And the determinant of an upper triangular matrix is just the product of its diagonal entries. So this is 4 times 1 times negative 2 times 3. So here it looks like I get negative 24. 5 says given the following diagonalization, what are the eigenvalues and respective eigenvectors for A? And so what we need to see here is that if we're able to diagonalize this matrix A, we're taking A and writing it in a form P times D times P inverse. And this tells us that the diagonal entries of our matrix D are the eigenvalues. So lambda is equal to 4, 2, and 1. And the columns of P are the eigenvectors for the associated eigenvalues, which means that the eigenvectors would be, the first one would be 1, 0, 1. And I am going to say the first one because this is associated with that eigenvalue 4. I can't mix up that order. So this would be the first eigenvector. The second one is 1, 0, 0. This is associated with lambda equals 2. And the last eigenvector is 0, 1, 1. So you can express it this way, but that order has to be correct because these are really paired like this, and like this. All right, D says use the information from the previous part to write an expression for a to the 4th power. All right, so the idea here is that if I can diagonalize, then a to the 4th should be equal to p times d to the 4th times p inverse. We can see that because if we just took a to the 4th, which is a times a times a times a, and wrote that diagonal expression, p times d times p inverse, so on and so forth, that this is just identity, and this is just identity, and this is just identity, which is why it simplifies to p d to the 4th p inverse. However, in this expression, the reason this is valuable to us is because if D is a diagonal matrix, then raising a diagonal matrix to a power really is like raising the diagonal entries to the power. That's not true for some matrix A, but it is true for a diagonal matrix D. So a to the 4th would really be just our regular matrix P times 4 to the 4th, 0, 0, 0, 2 to the 4th, 0, 0, 0, 1 to the 4th, which is 1. Times my matrix P inverse. And this is the representation. And note, for full credit, you do have to show that you're actually raising these individual components to power and not writing something like the matrix to a power. Because that's really the value, is that we can do that operation. All right, 6 is find the eigenvalues and eigenvectors of the following matrices, and then express them in a diagonalized form, or for complex values, that P times C times P inverse. Or we can write NA if the matrix is undiagonalizable. All right, so let's look at the first one. First, we've got to find our eigenvalues, which means we have to take the determinant of 2 minus lambda, 3, negative 1, and 6 minus lambda. Remember, our steps in general are first to find the eigenvalues using a minus lambda I, finding that determinant, and finding out when is that thing equal to 0. And that's what we're doing in this step. So I find this determinant, it's 2 minus lambda times 6 minus lambda minus a negative 3 or plus 3. And then I'll expand these two pieces out. I will get 12 minus 8 lambda plus lambda squared plus 3. So this is lambda squared minus 8 lambda plus 15, which I see can be factored as lambda minus 5 and lambda minus 3. And the question is, when is this thing equal to 0? Well, it's equal to 0 when lambda equals 3 or lambda equals 5. So those are my two eigenvalues. So we've used the determinant of a minus lambda I equals 0 to find these eigenvalues. The next step is for each eigenvalue to solve a minus lambda I times x equals 0 for x, and thus find the eigenvectors associated with the eigenvalues. So when lambda equals 3, this matrix right here is just like taking this piece and putting in lambda equals 3. So that matrix there is going to be 2 minus 3, which is negative 1, times 3, negative 1, and 6 minus 3, which is 3. Now really, if I'm solving this homogeneous equation, I could write this thing augmented with 0 as well. But once again, because it's augmented with 0, and those don't change using row operations, I really don't need to write that. Now, of course, I can see that these two rows are multiple. In general, even if I couldn't maybe see that right away, I would understand that to be true. Because remember, I'm looking for non-zero x values that satisfy this homogeneous equation. So there have to be non-trivial solutions. And they're only non-trivial solutions if I have free variables. And since it's just a 2 by 2, to have free variables, these rows must be multiples of each other. All right, so that being said, if I really wanted to simplify it, I could multiply that first row by a negative, and I could add the first two rows together, and it would simplify to this form, which tells me that my equation this is generating is x1 minus 3x2 equals 0. So I'm trying to find the eigenvector, so some value x1 and x2. So I can solve this for x1 and say x1 is equal to 3x2. And I could write this if I wanted as x1 is 3x2 and x2 is a free variable. Thus the eigenvectors are any multiple of 3, 1. This would be an eigenvector. And once again, any multiple of that is also an eigenvector. So if you want to multiply both of these things by a third and call it 1 1/3, that would be a perfectly valid eigenvector. So that's the eigenvector associated with lambda equals 3. Now we look at when lambda equals 5, and we repeat that same process. When I plug in lambda equals 5, I get negative 3, 3, and negative 1, 1. Once again, I can really see that these two things are multiples of each other. And so I only need 1 to give me some information. I'm going to look at this second row this time. It says negative x1 minus or plus x2 is equal to 0, or x1 is equal to x2. So I'll write out my solutions now. I'll let x1 equal x2, and x2 be a free variable. So it looks like my eigenvectors here are any multiple of the vector 1, 1. That's my second eigenvector. So my eigenvectors are when lambda equals 3, the eigenvector is 3, 1. When lambda equals 5, the eigenvector is 1. And lastly, I'll write my diagonalization. Now that I know the eigenvalues and eigenvectors, I can say let A equal my matrix P, where the matrix P has columns of eigenvectors. So I'm going to start with 1, 1, and then 3, 1. And then D is the diagonal matrix, where the eigenvalues are on the diagonal. And because I put this eigenvector first, I need to put its eigenvalue first. So this would be my matrix D. And last, I could put P inverse here. Now, to find P inverse, I would take the inverse of this matrix right here. So this would be 1 over the determinant, which is 1 minus 3. And then I would switch the values on the strong diagonal and change the sign of the values on the off diagonal. So this would look like it would be negative 1/2, 3/2, 1/2, and negative 1/2. That would be my matrix P inverse. So I could write that in here. Clean up a little bit of my work, and this would be the diagonalization. All right, now we'll look at the second matrix, B. So right away, I have a little shortcut I can do. Because this matrix is upper triangular, I know that the eigenvalues are just those diagonal entries. So right away, I know that lambda equals 2 and 1 and 1. And so I have some repeated eigenvalues here. But I have to be careful. Sometimes when I get repeated eigenvalues, I can still diagonalize. So I really have to go through all the steps. And beyond that, the first step in this problem was to find the eigenvalues and eigenvectors, regardless if it was diagonalizable or not, and to state that result afterward. So we'll start off just by finding when lambda equals 2, let's find the eigenvectors. So once again, I'm looking at a minus lambda I, which is subtracting that eigenvalue on the diagonal. So if I subtract 2 on the diagonal, I get 0, 1, 0, 0, negative 1, 1, and 0, 0, negative 1. Once again, I could write this as augmented with 0, but I really don't have to. I'm going to go ahead and put this thing into RREF. So in this case, I'm going to take row 2 plus row 1 and get 0, 0, 1. And then I'll take R3 plus R2. And the result will be this. And when I look at the equation this generates, it looks like it generates x2 equals 0, x3 equals 0, and because there are no pivot positions in the first column, x1 is just a free variable. So my solutions look like x1 is free, x2 is 0, x3 is 0. So the eigenvectors are any multiple of 1, 0, 0. So that'd be my first eigenvector. Now, let's see if we can actually diagonalize this thing. When lambda equals 1, my matrix looks like 1, 1, 0, 0, 0, 1, and 0, 0, 0. So when I look at this matrix, it's already in RREF, so I'll go ahead and write out my equations right away. This says x1 plus x2 equals 0, and x3 equals 0. And it looks like x2, because it doesn't have a pivot position in that column, is a free variable. So my solutions look like, well, x1 should be equal to negative x2, x2 is free, and x3 is equal to 0. So the eigenvectors here are any multiple of the vector negative 1, 1, 0. Well, that's a perfectly valid eigenvector. However, because this eigenvalue was repeated twice, for me to be able to do the diagonalization, I need the dimensions of this eigenspace to be 2. But right now, this eigenspace is just generated by any multiple of one vector. It only has one basis for the eigenspace. I needed to get 2 eigenvectors here, and I didn't get them. So this tells me this is not diagonalizable. All right, now we're on the last one. So in this case, we're once again going to find the eigenvalues first. So I'm looking at the determinant of 2 minus lambda, 4, negative 1, and 2 minus lambda. So I have 2 minus lambda squared minus a negative 4 or plus 4. I'll expand this out. I will get 4 minus 4 lambda plus lambda squared plus 4, or lambda squared minus 4 lambda plus 8. And the question is, when is this equal to 0? Now in this case, I really can't see a nice way to factor this. So I'm going to have to use the quadratic formula. That tells me that lambda is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's put in these values. B is negative 4. So negative 4 is 4, plus or minus the square root of b squared minus 4 times a times c. This is 32. All divided by 2a, which is 2. We'll simplify this to get 2 plus or minus. We have 16 minus 32 is negative 16, and the square root of negative 16, is going to be 4i. 4i divided by 2 is 2i. So looks like my eigenvalues are lambda equals 2 plus or minus 2i. I have complex eigenvalues. All right, so now to find the eigenvectors, I'm going to start by using lambda equals 2 minus 2i. I'm going to plug that into my equation. So I will get 2 minus the quantity 2 minus 2i, 4, negative 1, and 2 minus the quantity 2 minus 2i. Now instead of doing any kind of row reduction here, I'm going to realize that for there to be non-zero eigenvectors, these two rows have to be multiples of each other. So I'm just going to grab one of the rows. In this case, I'm going to choose to grab the first row. So I'll simplify that a little bit. This says 2 minus 2 is 0, and minus 2i is positive 2i. So this tells me I have 2i times x1 plus 4x2 is equal to 0. And if I want, I can go ahead and solve this thing for x1 or x2. In this case, it's easier to solve for x2 because I don't like having to try to divide through by these complex numbers. When you do this with complex values, you have to be careful with your negative signs. So in this case, I'm just going to solve it for x2. I will subtract x2 to the other side and divide by negative 4. The result being negative 1/2 I, or negative I over 2, times x1. I'm going to use this to generate my eigenvector now. So my eigenvector, which is some x1 value and some x2 value, in this case I'm treating x1 like it's the free variable. Once I pick a value for that, I would know what x2 is. x2 is negative I over 2 times x1. So this looks like any multiple of 1 and negative I over 2. Now I really do mean any multiple here. So let's just show you some other forms of this vector that would be perfectly acceptable. I'll choose some values to multiply this vector by. If I chose x1 to be 2, for instance, this would simplify to 2 and negative I, which would be a perfectly valid eigenvector. If I chose to multiply this by 2i, for instance, well then I would have 2i up here. But when I multiply this bottom part by 2i, the 2's would cancel out. I times I is negative 1, and I would get left positive 1. So this would be another possible value. So from here you can kind of see the two constructions, and any multiple of any of these would also be a valid eigenvector. So if I just choose this one kind of randomly as the correct eigenvector, then I'm going to rewrite this into a real part and imaginary part of the vector. I can rewrite this as 0, 1 as the real parts, plus I times 2, 0, the imaginary parts. It's that same idea of how we take our solution vectors and write them in parametric vector form, but I'm just separating the real and imaginary parts. So if that looks a little ugly, just take this, multiply through the second vector by I, and actually add the two vectors together, and you'll see we get back to where we started from. So I'm just rewriting that eigenvector in a different form. But the reason I want to do that is so I can identify the real part of that vector and the imaginary part of that eigenvector. Because if I have that real part and the imaginary part, and the real part and the imaginary part of my eigenvalues, now I can create that, not quite a diagonalization, but this factorization for my matrix A. A in this case should be P times C times P inverse, where P is a matrix where I have columns as the real part of my eigenvector and the imaginary part of my eigenvector. And then I have the matrix C, which is a rotation matrix, where I have, in general, it looks like A, negative B, B, and A. But in this case, my A value is 2, and my B value is also 2. So this looks like 2, negative 2, 2, and 2. And lastly, I would just have P inverse here. And I can take a second real quick to calculate what this P inverse would be. It would be 1 over the determinant, which would be 0 minus 2. And I would switch the strong diagonals and put a negative sign on the off diagonals. So this would look like 0, 1, 1/2, and 0. So that P inverse would be 0, 1, 1/2, and 0. And so this would be the correct factorization using these complex eigenvalues and vectors. All right, and that concludes this video key for exam 2. Thank you.